Hello everyone, welcome to our lecture on a fundamental concept in nutrition, energy intake. Today we will be covering the material from chapter 2. We will explore what energy is, where it comes from, how our bodies use it, and how we measure and estimate our daily needs. Understanding nutrition balance is the cornerstone of nutrition science and practice. So let's begin. Let's start with the most basic question: what exactly is energy in the context of nutrition? So, what is energy? At its core, energy is simply defined as the capacity to do work. The ultimate source of all energy for life on Earth is the sun. Through photosynthesis, plants capture this solar energy and store it in the chemical bonds like glucose. When we as a human consume plants or consume animal that have eaten plants, we are accessing this stored of energy. Our bodies are designed to metabolize the chemical energy found in the macronutrient, carbohydrates, protein, and fats, as well as alcohol. This energy is not just a movement, it fuels every single process in our body. The complex chemical reactions that build and repair tissues, the electrical impulses that allow our nerves to communicate, and the mechanical work of our muscles, and the heat production required to maintain our core body temperature. Now that we have foundational understanding of what energy is, let's discuss how we determine how much of it we actually need. So this brings us to concept of energy requirements. So the defining energy requirements. An individual requirements is the amount of dietary energy they need to consume to maintain their current body functions and, if applicable, support growth. This isn't a single number that applies to everyone. It's highly personalized based on the factors like age, gender, weight, height, and very importantly, physical activity level. We also have considered special circumstances like in children, pregnant and lactating women. Energy requirements include the additional energy need to build new tissues and produce milk. Furthermore, clinical setting, illness or injury can act as a significant stressors that dramatically alter person's energy need, either by increasing them due to heightened metabolic stress response or by decreasing them in some conditions. A common tool we use to gauge energy balance is body weight. So a common tools to calculate, to determine, to evaluate the energy balance is a body weight, but as well as see in the next slides, while it's useful, it has some significant limitation. So over long term, body weight is a reflection of energy balance. If you consistently consume more energy than you expend, you gain weight. If you consistently expend more than you consume, you lose weight. It is a simple concept. So when I can gain weight, when I can lose weight, depend on the energy consumed. Consumed less than I need, consume more than I need. However, we must be cautioned. Body weight is not a reliable indicator of the quality of diet. A person can be weight stable while consuming a diet severely lacking in essential vitamins and minerals. Moreover, body weight can be misleading because it doesn't distinguish between lean mass, like muscles and organs, and fat mass. So, two people can weigh the same, but the one with more muscle will have higher energy requirements, and the second more fat, so will have low energy requirement than the first. This is also why individuals with obesity have higher energy need. They carry not only more fat mass but also more lean mass to support that larger frame. So because some fat person also have more muscle in the same time. So to get clear picture, we need to break down our daily energy use into its core component. So our total energy expenditure, or TEE, is made up of three parts. The first is a basal resting energy expenditure, and the second, thermic effects of food and activity thermogenesis. So every day your body total energy expenditure, or TEE, can be broken down in three main categories. First, and the largest, is a basal metabolic rate or resting energy expenditure, PEE or REE. This is the energy your body burns just to stay alive, for things like breathing, circulating blood, and basic cell function, even when you are completely at rest. The second is thermic effects of food. This is the energy your body uses to digest, absorb, and metabolize the food you eat. And the third is the activity thermogenesis, which is the energy you expend during any and all physical movement. So the simple formula to remember is TEE, total energy expenditure, equal to resting energy expenditure plus thermic effects of food plus activity thermogenesis. So let's take a closer look at that largest component, resting energy expenditure. It's important to understand the subtle but important difference between basal and resting energy expenditure. Basal energy expenditure, or basal metabolic rate, represent the absolute minimum energy required to keep you alive. To measure it accurately require extremely strict laboratory condition. The person must be in a thermoneutral environment, completely at rest, both physical and mental, and have fasted for 10 to 12 hours is better. The resting energy expenditure REE or resting metabolic rate RMR is similar but measured under less stringent condition. It's the energy need to sustain normal body function at rest. Because the conditions are less strict, the REE is typically about 10 to 20% higher than the BEE. In practice, especially in a clinical setting, these terms are often used interchangeably, with REE being the more commonly measured value. So, what determines a person REE or resting energy expenditure? Many factors contribute, but let's start with the two most significant: body composition and age. The primary predictor of your resting energy expenditure is your body composition, specifically your amount of fat-free mass or lean body mass. This includes your muscle, your organs, your bones, and connective tissues. These tissues are metabolically active and burn calories even at rest. In fact, your lean body mass accounts for about 80% of the variation in resting energy expenditure among individuals. This is why athletes with their greater muscle mass have about 5% higher resting energy expenditure than non-athletes of the same size. Regarding to the age is another critical factor. Resting energy expenditure is at its peak during period of rapid growth, especially at the first couple of years of life. After we reach early adulthood, our lean body mass naturally begins to decline, and with it our resting energy expenditure drop by about 1 to 2% per decade. The good news is that regular exercise can help preserve that lean mass, keeping our metabolically rate higher as we age. Within our lean body mass, some tissue are far more metabolically active than others. So let's look at which organs are the true energy powerhouses of the body. Here are the factors affecting resting energy expenditure. We want to talk about the organs. While we often associate metabolism with muscles, it's actually our major organs that do the heaviest lifting at rest. These are known high metabolically rate organs, and they include the liver, the brain, heart, spleen, intestines, and the kidney. As you can see from this figure, although these organs make up a small fraction of our total body weight, they are responsible for approximately 60% of our resting energy expenditure. This helps explain why two people of the same weight, age, and highest can have different resting energy expenditure. Small variations in the size of these organs can have significant metabolic impacts. Beyond our internal composition, other physical characteristics like body size, climate, and gender also influence the resting energy expenditure. So it's intuitive. The larger people generally have higher metabolic rates than the smaller people. So the body size, one of the factors that affecting resting energy expenditure. But it's also about the shape. A tall, thin person has larger body surface area compared to the short. So stocky person of the same weight, this large surface area means more heat is lost to the environment, requiring higher metabolic rate to maintain body temperature. The climate also plays a role. People living in a tropical climate can have resting energy expenditure are 5 to 20% higher than those in temperate zone. Exercising in extreme heat also adds a small metabolic load. Finally, regarding to the gender, men instead of women, men typically have 5 to 10% lower than women have 5 to 10% lower than resting energy expenditure for men, or I can say men typically have 5 to 10% higher than resting energy expenditure than women. Now let's turn to our attention inward or to the body's internal environment, specifically our hormones and core temperature. Our hormonal status is a powerful regulator of metabolism. Endocrine disorders like hyperthyroidism or hypothyroidism can cause significant increase or decrease in resting energy expenditure or basal metabolic rate. Stress hormones like epinephrine and temporarily boost cellular activity. A woman's metabolic rate even fluctuates slightly throughout her menstrual cycle, and pregnancy lead to gradual 15% increase in basal energy expenditure to support the growth of a new tissue. And regarding to body temperature, or can I say fever, body temperature has a direct and predictable effect for every degree Fahrenheit or the degree centigrade. For fever above normal, the resting energy expenditure increase by 7%. That's 13% increase for every degree Celsius. This is a critical factors to consider when determining the energy need of a sick or ill patient. To round out our discussion on factors affecting resting energy expenditure, let's look at the few external substances and clinical conditions. Certain substances we consume can act as stimulants and temporarily increase our metabolic rate. The most common is caffeine, nicotine, and alcohol. Our overall clinical state is also crucial. Severe stress, such as from major surgery or trauma, can significantly increase energy expenditure. Conversely, conditions like starvation or chronic dieting can depress the metabolic rate as the body attempts to conserve energy. Understanding these factors is essential for providing proper nutrition support in a clinical setting. Okay, that covers the largest component of energy expenditure in detail. Let's now move on to the second component, the thermic effects of food. The thermic effects of food, TEF, is the energy your body expends to process the food you eat. This includes digestion, absorption, transportation, and storage of nutrients. It accounts for a relatively small but consistent portion of your total energy expenditure, typically around 10%. Interestingly, the thermic effects of food varies depending on the macronutrient composition of a meal. Protein has the highest thermic effects of food, meaning your body burns more calorie to process it, followed by carbohydrate and then fat. So this is important information. Protein has the highest thermic effects of food, then carbohydrate, then the lowest is fat. Certain substances like capsaicin is in spicy food and caffeine can also enhance and prolong the thermic effects of food. It is also important to remember that clinical nutrition support like tube feeding or IV nutrition also has a thermic effects. We've now covered our resting metabolism and the energy of digestion. The final and most dynamic piece of the puzzle is activity thermogenesis. The activity thermogenesis is by far the most variable component of our total energy expenditure. This is what creates the vast difference in daily calories need between sedentary office workers who might only expend 100 extra kilocalorie a day and elite athletes who could burn an additional 3000 kilocalorie. So activity thermogenesis can be broken down into two types. The first is exercise, which blend structure physical activity. The second is which is often overlooked but very significant, is non-exercise activity thermogenesis. It includes all energy expended during our activities of daily living, things like walking to your car, doing anything in light activity, fidgeting at your desk, even maintaining posture. So understanding these components is key, but how do we actually put a number on them? Let's discuss the scientific methods and the unit used to measure energy expenditure. So measuring energy expenditure unit and methods. The standard unit we use to measure food energy is the kilocalorie, often just called calorie, just capital C, on food label. In other part of the world and in scientific literature, you may also see energy measured by joule or kilojoule. The conversion is straightforward. 1 kilocalorie is equal about 4.2 kilojoule. There are two primary scientific methods for measuring the human energy expenditure. Maybe the first primary method is direct calorimetry and indirect calorimetry. So this is the two primary measurement of the energy, by direct calorimetry or indirect calorimetry. So let's compare these two methods to understand how they work and which is more practical for everyday use. The direct calorimetry is exactly what it sounds like: a direct measurement of heat. A person is placed inside a specially constructed airtight chamber, and the amount of heat their body gives off is measured. While it's highly accurate, this method is extremely expensive, complex, and require the subject to be confined, which doesn't reflect real world free living condition. For these reasons, so indirect calorimetry is the much more common and practical methods used in both clinical and research setting. Instead of measuring heat directly, indirect calorimetry measure energy expenditure indirectly by quantifying gas exchange, specifically how much oxygen a person consumes and how much carbon dioxide they produce. From these values, we can accurately calculate their energy expenditure. To ensure the data from indirect calorimetry is accurate, it is essential to follow a strict measurement protocol. For this table outlines the key steps for reliable resting energy expenditure measurement. A fast of at least 4 to 7 hours is required to ensure that thermic effects of food is not influencing the reading. Stimulants like caffeine and nicotine must be avoided as they artificially elevate metabolic rate. Likewise, there should be no recent exercise before the measurement, being the individual should rest quietly for 20 to 30 minutes to achieve a true resting state. The environment itself should be calm, quiet, and comfortable. Following this protocol is critical for obtaining a valid and useful measurement. One of the most valuable piece of data we get from indirect calorimetry, besides the resting energy expenditure itself, is the respiratory quotient. So the respiratory quotient, RQ, is the ratio of carbon dioxide produced to oxygen consumed. This simple ratio gives us powerful insight into what kind of fuel or substrates the body is primarily metabolizing at the moment. The RQ of one indices or one indicates that body is primarily burning carbohydrate, but RQ value 0.85, that means mixed diet. When RQ value is 0.7, indicates fat is the primary fuel source. A mixed diet of carbohydrate, as mentioned, 0.85. Clinically, RQ greater than 1 can be a red flag for overfeeding, as it suggests the body is converting excess of carbohydrates into fat. A very low RQ below 0.7 can indicate ketosis, often from inadequate nutrient intake. While indirect calorimetry is a clinical standard, there are even more sophisticated methods used primarily in the research setting. The gold standard of measuring total energy expenditure in a free living individual not confined to the bed is a doubly labeled water, DLW. This method, a person drinks a dose of water containing safe, stable isotopes of hydrogen and oxygen. By tracking how quickly these isotopes are eliminating from the body over 1 to 2 weeks, researchers can precisely calculate total energy expenditure. However, its high cost and complexity make it impractical for clinical use. Other methods to estimate the activity component include triaxial monitor. Triaxial monitor or accelerometers measure the movement to estimate activity. And physical also activity questionnaire. Questionnaires are simple and inexpensive, but are not prone to self-reporting errors. Since direct measurement isn't always possible, we often rely on predictive equations to estimate energy needs. So let's review the most common equations, the most common ones. Harris-Benedict equations in 1919, Mifflin equations in 1990. For many years, Harris-Benedict equations were standard. However, extensive research have shown that they tend to overestimate resting energy expenditure, sometimes by as much 27%. Therefore, their use no longer recommended. The current most accurate and evidence is Mifflin equation. They have been validated as the most reliable for estimating resting energy expenditure in healthy adults, including those with obesity. As you can see, there are separate formulas for males and females which use weight in kilogram, height in centimeters, and age in years. Once we have estimated resting energy expenditure from Mifflin equations, we still need account for activity to find a total energy expenditure. A simplified practical way to estimate total energy expenditure is to take the resting energy expenditure, whether it's measured or calculated, and multiply it by the activity factor. This table gives you general range. For sedentary, the individual with desk job and minimal movement, you would add about 10 to 20% to their resting energy expenditure. For someone with a moderate active lifestyle, you might add 25 to 40%, and for some engaged strenuous activity like construction workers or competitive athletes, the increase could be 45 to 60% or even higher. This is a quick estimation methods commonly used in practice. The estimated energy requirements is official methods developed by the Institute of Medicine as a part of Dietary Reference Intake (DRI). The goal of estimated energy requirements is to predict the average dietary intake need to maintain energy balance and good health in a person of a specific age, specific gender, and weight, height, and crucially defined physical activity level. These equations are more complex than simple activity factor we just saw because they are derived from data using the gold standard, as mentioned before, doubly labeled water methods. There are specific estimated energy requirements equations for very life stages group, from infants to older adult, as well as for pregnancy and lactation. Let's look at some sample estimated energy requirements value to get a sense of the recommendation. In this table shows an abridged summary of the estimated energy requirements for various life stage group. Start from 0 day to 6 months, then 7 to 12 months for children 1 to 2 years, 3 years to 8 years, 9 to 13 years, and 14 to 8 years, and adult more than 18 years. And for pregnant women, first trimester, the second trimester, third trimester, and age of the adult from 19 to 50 years, and also lactating women, and so on. So this table shows an abridged summary of the estimated energy requirements for various life stage group, assuming they are healthy and have an active lifestyle. You can clearly see how energy needs change throughout lifespan. Breaking the peaking in late adolescent males, maybe for males instead of female, the peaking. You can also see the significant additional energy requirements for the later stage of pregnancy, third trimester. Here you can see, and lactating women. Keep in mind these are just averages for a reference size person. Individual needs would be calculated using a specific estimated energy requirements formula. A K input for energy ER equations, or estimating energy requirements equations, is the physical activity level. Or so let's see how that is categorized. The physical activity levels categorized depend on sedentary lifestyle, low active, active, and very active. So it is the ratio of their total energy expenditure to their basal energy expenditure. The dietary reference intake framework defines 4 categories: sedentary, low active, active, very active. To make these categories more tangible, the table provides a walking equivalence. For example, low active lifestyle is roughly equivalent to walking about 2.5 kilometer or 2.2 miles per day at moderate pace, in addition to light activity of daily living. An active lifestyle is equivalent to walking over 7 miles per day. This helps us to classify an individual's activity level to select the correct coefficient for estimating energy requirements equations. Another common way to quantify the intensity of specific activities is by using metabolic equivalent, or METs. Metabolic equivalent are a simple or practical unit for expressing the intensity of physical activity. So 1 MET equal resting metabolism 1 kilocalorie per kilogram per hour. So ONMET is defined as the energy expenditure of the body at rest. So an activity in MET value of 4, for example, require 4 times the energy of sitting still, as you can see from the table lying quietly in 1 MET. A moderate walks 3.3 and vigorous activity like jogging about 10 METs. METs value can use to estimate the energy cost of a person's daily activity in more detailed way. So we've focused heavily on the expenditure sides. The expenditure side of energy equations. To complete the picture, so let's briefly look at the intake side, calculating energy in food. So in laboratory, to calculate the food energy, in laboratory the total or gross energy content of food is measured by using a device called pump calorimeter, which literally burns the food to measure the heat released. However, our bodies are not 100% efficient to digestion and absorption. Therefore, we use metabolizable energy values, which account for these losses. These are the standard values used in nutrition that you should commit to memory. Carbohydrates and protein each provide 4 kilocalorie per gram, while fat provide 9 kilocalorie per gram and alcohol provides 7 kilocalorie per gram. So these are the number used to calculate the calories content you see in all food label. This brings us to the end of our chapter, so let's quickly summarize the most point to take away. To wrap up, let's review the key concept. First, energy balance is the foundation of weight management. Our total energy expenditure is the sum of 3 components: our resting metabolism and thermic effects of food and our activity. Resting energy expenditure is the largest component and is primarily determined by our lean body mass. We can either measure energy requirements accurately with indirect calorimetry or estimate them using validated equations, with Mifflin equations being the current standard. And finally, remember that person with physical activity level is the most variable and also the most controllable component for their daily energy expenditure. Thank you for your attention and see you in the next lecture.